I can hit the buttons. Is all that matters.
That's up to you. You prefer it up here.
It'd probably be better over here. Stand off to the side.
Okay.
Yeah, I guess that works. Sweet. Am I able to leave the screen or no?
What?
Oh,
Yeah.
wait. Okay.
So right now we're broadcasting, but I will screen share when you're ready to start. I'm just going to do the intro stuff.
Wait, if I hit the arrow keys, will it move the thing or not?
I'll make sure it does.
Okay.
I'll get onto your thing before. And then I'll take
that was basically my only question.
All right, cool.
Can I move the slide? Because otherwise I could give the talk only on this slide, but it would be very interesting.
All right. Cool.
Wow. A lot of people.
Hello.
Hey.
Hey guys. How you doing?
Great to meet you.
So welcome to the People in the AI group. We're back after kind of a short break. I think so. Right now we have 3 really cool talks coming up tonight. Bobby's going to talk on Draft Network. Remesh is going to talk on what they do, and then Ian, who's our first person presenting from out of town. He's in Halifax, Canada. He'll be presenting on AI as an engineering product. Quick recap of what we do here at Cleveland AI. The whole idea is AI is an exciting new technology, and it's really interesting and fascinating. But people in Northeastern Ohio don't know about it or don't know how to do it, and want to use it in their businesses and want to use it for things probably much more than just business. And right now, we don't really know how to. So the idea here is that we give these talks and try to help out with different events in town to help get people up to speed, and hopefully the companies that are trying to hire here will be able to find talent. Once people get a hold of some of this stuff. So I presume all of you are interested in that in one way or another. So thank you for coming out. I really appreciate it, and I'm happy that this is growing and that people continue to show up to me. So the first thing we do normally, we do 2 things. One, community updates. So for people who are part of other meetup groups or anything like that, we do announcements like that. And then second, we do recruiting shout-outs. So if you are part of a company or an organization that's hiring or looking for people, we do a shout-out like that so that we all are aware of what's going on in the city. But first, if we want to do community shout-outs, if anyone has them, now would be the time. And just kind of raise your hand and we'll just go through them. Cool.
My name is Andrea. I work across the street actually at Tech Elevator. We're a 14-week coding boot camp. Some of you have heard of us. We're working at companies who have hired our graduates. Happy to launch our fall cohort, which is crazy to think it's already fall. But I wanted to stop by tonight because you're so close and let you know about a couple of training classes that we just added to the schedule. I'm sure a lot of you know Pandata. We partnered with Pandata to offer 2 different data science sessions, training sessions coming up in November and December. There is early bird pricing until early October. And we're also giving a discount exclusively to this meetup group. So I wanted to pass it along if you were interested in learning more about data science. The one workshop is a 3-day workshop, Intro to Data Science, where you learn the core concepts from Cal himself, the chief data scientist, and Hannah, who works there. The other workshop that we're doing is a 2-day data visualization and dashboarding workshop. So a little bit shorter, different concepts, but obviously same overlap with data science being the main theme. Hoping to contribute back to some of the talent, as we talked about, hopefully getting people more placed and excited about data science in Cleveland. Lots of stuff happening right now. So we're excited to offer training sessions. I will leave this with you. This is basically all of our training sessions, and you'll see the data science ones on here. I'll just leave it back here if you want to grab one if you're interested on the way out. And then if you, I think we sent you the code. You have the code. So if you want the code, it is data group. We'll give you 25% off, which is a pretty big chunk of change off these guys. So data group is the code to use until the end of the month, so the next couple of weeks. If you forget it, I'll send Jason my specific contact info, so you can always reach out to me, ask questions, or reach out to Pandata, Cal, anyone on the team, Nicole, and help answer anything else. Thank you so much for giving me a chance to say hi. Stop by Tech Elevator next time you're in the neighborhood right across the street at the big. Thanks, guys.
Anyone else have an option? Cool. We also have at the AI group, we're going to be doing a study session as well on Fast AI. It's a little bit different than what they're doing. It sounds like something custom for data science 101 and data visualization. Fast AI is more around deep learning, which is kind of like our core modern artificial intelligence and the stuff a little bit closer to research. We didn't develop the course. We're going based off the course that was developed by Jeremy Howard, who is involved with Caig and a number of other startups. Very successful. And they're one of the most well-known organizations doing education for AI. It's all free online. We will be hosting it for free. And we're essentially just here to help support anyone who wants to do it. And it's definitely one of the most well-recognized ways of getting started. It doesn't assume any mathematical knowledge beyond high school math. It does assume that you know some coding, in particular it uses Python. But Python can be pretty easy to transfer to if you know other languages. So I definitely recommend you check it out. The first meeting for that is on Monday. It's going to be hosted by Michal and then Michael and Brendan, who are here today. If you're interested, definitely sign up on our meetup page or talk to them specifically if you have any questions, because they went through it over the summer with me all, and they've all kind of worked on it. So.
And it's at Tech Elevator, like right across the street.
It's also Tech Elevator. That's Monday at what, 6 p.m.?
Yeah, I think 6 to 8 is when we're actually going to be doing material.
Cool. And they'll have pizza, and it's being sponsored by the Python software. So, also, while we're at it, shout out to Remesh and Caig for having us. Remesh, who will be talking later, helps get the space here today, and really good to do it. With that, if you want to go to employment announcements, anyone who's recruiting or hiring, anything like that. Cool.
I work for a company called Embrace Pet Insurance. We have a couple of positions open. We sell pet insurance, but we're very much a tech company, and market's huge. We're growing like crazy. We've got a couple developer positions, like software developer positions open, but the one that probably interests most here is we do have a mid to senior level, like database developer BI position. We're just now setting up like a true data warehouse environment. We want somebody to take it, finish it, make it their own, and run with it, and do some reporting stuff in Tableau and SSRS and ETLs and so forth. If you want any information, hit me up or shoot me an email at nal@embracepetInsurance.com. The benefits or perks are awesome. It's a great company to work for.
Thanks.
So we have two jobs. I work at a media company. My name is Charlie. I need the card after. I don't have any paperwork. But so we have two jobs. One is a data person who can understand our data and work with our sales. So to help them understand it, because our salespeople don't really understand our data. We have a lot of data, and so help them sell it. The other is more of a traditional sort of data scientist job, which is to deep dive into the profiles. We have millions of profiles. We started off as a publishing company, and now obviously we're on the web. And so we have millions and millions of profiles that we have not had anybody really dive into. So do those roles. I'll be after. I can give you cards.
What's the name of your company?
Meister Media. Meister. MEISTER. The one job's actually on the website in case somebody doesn't catch me afterwards.
Cool.
My name is Chris McPherson. I'm a data scientist at Really Tiger, actually across the street every day. We do a data engineer badly. We've got a lot of machine learning models to get kind of medium into these things, but of course, there's a big engineering pipeline to support them and productionize those models. So we're using some of it as a Python equivalent to develop pipelines.
Anyone else have any employment announcements or anything like that? Cool. If anyone forgot anything, or if you want to post the ones that you just talked about, feel free to post comments on this event page. It'll blast notifications to everyone who signed up for the event. It's a good way to kind of remind people who may have been interested but may not have been able to catch you before we ended. So with that, I think we're ready to go. If Bobby's ready to go?
Yep.
Bobby's ready to go. So, yeah. Bobby Wagner, in case he's doing graph networks.
The error keys working now.
Oh, good point. That's what I forgot to do.
Okay, cool. Hi everyone, I'm Bobby. I'm a senior at Case studying computer science, and I'm here to talk to you about using neural networks with graphs. Graphs, over the course of this talk, I'm going to talk about why you should care about this at all, like what are graphs, go over what is convolution, and then talk about graph convolutional networks. So graphs are a data structure that encodes the relationship between objects. The objects being like A, B, C, and D, and the relationships being the lines between them. This is important because the relationships between things often give us more information about the things themselves. Many things are represented as graphs, like social networks, maps, neurons. Technically, images are a special class of graphs, and many, many other things. And like I said earlier, we can gain a lot of information from this structure. So before we talk about how you can use the graphs that you have in your deep learning pipelines, first I'm going to go over how you represent graphs. There's two parts of graphs. There's the features about the objects themselves. This is pretty similar to what you probably have already if you're doing any machine learning. You have objects and features about those objects. These are your training examples. Like it says, you probably already have this. And if not, there's plenty of places on the website on how to curate data. Where graphs shine is they also have relationships. There's two main ways to convey relationships, being adjacency lists and adjacency matrices. An adjacency list just tells you which other objects are nearby. It's very efficient for storing sparse graphs, but because it's not differentiable, you can't use it in like a deep learning pipeline because you can't pass the gradients back through. On the other hand, adjacency matrices are able to be differentiated. They store the data in the form of an n by n matrix, where n is the number of nodes. And at every point, if those two nodes are connected, like there was an edge in the previous drawing, there'll be a 1 there. And if there isn't, there'll be a 0 there. It stores it. It takes up a lot more space than a list because you have to store all those zeros if most of them aren't ones. But because it's differentiable, you can use it with neural networks. There have been some advancements in recent days with storing sparse neural networks and doing inference on them, which should hopefully remedy that issue. Next, I'm going to go over what convolution is, so we can get to the meat of this talk. What convolution is an operation that takes the neighbors of an object, applies some transformation to them, and then sums the result up to get the result for that one object. This is typically used in image processing. As you can see on the screen, what you're doing is you look at all the cells near the cell that you care about, multiply it by what's called a kernel matrix, which just tells you how important each of the neighbors is, and then you get an output, which is the sum of those results. Now we're going to talk about extending this to be used with graphs. All right, so next we're going to talk about graph convolutional networks. So we want to learn a function that encodes that the output is some function of the input, with the input being the features of the graph. And we want to use the structure of the graph to help learn that function. So we can learn this by having an arbitrary weight assigned to each node or each relationship in the graph of how much that relationship contributes to the output. And then if we multiply that by the adjacency matrix we had earlier, that weight is only used when we're in one of the, when that connection is actually active. Because otherwise it's 0 and gets ignored. And then we further multiply that by the features to get the sum over all the adjacent matrices. Since it's matrix multiplication, you do the pointwise multiplication and then sum up all the results. And then finally, we apply a nonlinearity to this so that we can learn more than linear functions. And that's basically the meat of this talk on how you use graphs. So much so that I made a slide for it. What you want to do is you simply take the structure of your graph, you multiply it by the weights you're trying to learn, and then multiply it by the features, and then you get your output. And since this is all differentiable, you can use backpropagation to pass the data, or the data back through to update those weights. There's a couple improvements we can make to this model on how you treat the adjacency matrix in order to make it perform better. The first one we want to do is we want to scale each of the adjacency matrices so that they all add up to 1 for each node. This prevents it from nodes that have lots of connections going into them from gaining stronger weighting. And so it scales more appropriately. And then another option that you can do is if you want information from nodes that are further away from the node you're looking at, you simply add more of these layers. Because if you run the same procedure on the new updated layer, you then get the information from further away. One other thing that I didn't put on the slide is that for this adjacency matrix, you most of the time want to add the identity matrix to it so that every node's connected to itself. Otherwise, you don't get the information about the node itself. There's some future research that needs to be done on this that has to do with how you deal with some of that structural data is missing. Because in the ideal world, you'd have a complete graph for all the data you care about, but we most of the time don't have that. And then also, the learning procedure of this is kind of slow, because unlike with image convolution, we don't reuse the weights. Some recent research has gone into that, but that's not going to be covered during this talk. So to finish up, here's how you can use this with your current data. You want to get that structured data about your data. How you get that really depends on the problem, but most of the time should be fairly obvious, because it's just the relationships between the things that you're trying to learn about. You take that formula that we talked about earlier, and you create a layer in your architecture that applies that formula. And then you train it like you would normally. You can also use more than one of these structures within your graph. Say, for example, you have a graph of who's friends with who and who's following who. Since you can have them independently be calculated, learn their own weights for how much that data matters, and then sum those results, multiply those results, basically anything you can do with any other data. And then also the feature matrix that we talked about earlier can also be learned representations. Since we're able to backpropagate through these layers, we can do anything we would in a normal neural network for the features. So in conclusion, graph convolutions are still in a fairly early stage. There's a lot of research to be done, but even now with the simple state of research, they can be leveraged to get insights from the structure of your data. That's all I have for today. So if anybody has any questions, yeah.
Yeah, trying to make sure I got it correctly. So is the matrix A, it's part of your input or it's part of the W's?
The matrix A is something that you know that you're not learning. It's something you know out of stream. Yeah, the matrix A is just the relationships between the data. So you get that from whatever your data source is.
So if we make this concrete, right? Let's say you have a Facebook account and you have a list of Facebook friends. So you're friends with all these people. So that's like you have relationships with all these people. That would be like an adjacency. Like that'd be an element of the adjacency matrix, but then all these people have relationships with each other potentially. So that could be like for each of those nodes, those also have adjacency elements, I guess.
Yeah.
And so the adjacency matrix is if you take all these nodes and kind of lay them out, like here's like all those nodes, and here are them again, copies. You can see which nodes are related to each other by this size of this matrix. But
yeah, that's exactly it.
Just want to make sure I understood you. You said we couldn't reuse the weights for graph convolutional networks on like image. Can you
So
explain that a little bit more?
yeah, with image convolution, I'll go back to the slide for it. Most of the time you're learning this kernel matrix, which is the same for every node. It saves on data, somewhat speeds up learning. With graph convolutional networks, because there's less defined structure, like each node doesn't have a guaranteed 4 neighbors, you can't necessarily do that type of thing. So you have to learn weights for each of the relationships.
Okay, thanks.
so technically, this is a locally connected.
Yeah.
Right. So when we say like, oh, I use a convolutional layer, it normally really means I use a locally connected layer. Convolutions don't require weight sharing, right? Weight reusing, but locally connected layers do. So if you look at like CS231N, which is Andre Karpathy's course at Stanford, they go over the difference there. Most courses gloss over this difference, but here it actually matters.
I'm sorry, what class was that?
The Stanford vision class.
Okay, thanks.
So you were saying like the features are learnable, right? Like so maybe I'm just not sure, but like is there an advantage to this over like collaborative? Like is that like am I getting that right? Like, are there similarities in like the applications?
I'm not actually very familiar with collaborative filtering.
So like like if I wanted to like estimate or like do like a recommender system, right? So like if the graph is sparse or like the matrix is sparse because you lack of connections, like you can use collaborative filtering to estimate like the strengths or like suggestions. Does that make sense? Is that like a similar application of this? Like can you use that in a similar context, or am I just completely off? Does that make any sense?
Yeah, to me it sounds like it could be used in some
Okay.
context.
Yeah, I think this is abstract away from what you're predicting, right? So as long as you have a graph data structure, it seems like this could be applicable as long as you have the data for it.
So sorry, I'm just gonna keep going. So yeah, so like are you trying to predict like the strength of the like the connections, like the
Yeah, what you're learning
edges?
here is how much each of the edges matter for what you're trying to predict.
Okay, so it's just and I'm reducing down to like it's a neural network for like a patient, right? Like
Yeah,
it's just a different estimator.
Yeah, it's a
Sort of.
yeah.
Okay.
I think what's interesting about this is that the feature matrix that you use, right, can be the output of a previous graph convolution, right? So you can get the like neural network effect where like you can compose like higher level features on top of like lower level features and learn that whole representation.
Yeah.
So you can apply it to a graph structure which previously hasn't been done.
Yeah, it seems much more descriptive.
It's a more generalized approach of a lot of things that have been tried already. And the fact that the math is so simple is kind of amazing.
Actually, I have seen, so people are using this already. Last year at NIPS, NIPS is the Neural Information Processing Systems Conference. It happens every year. It's like the largest conference on deep learning and neural networks in particular, which is driving AI right now.
It sold out in 11 minutes this year.
Sold out in 11 minutes. None of us got tickets.
Yep.
But so at the Machine Learning for Healthcare conference or workshop that they had on Saturday, which is at the end, they do workshops for specific topics. There was one in particular that I saw that was really interesting where they used graph convolutional networks on drug data from FDA. So they had all these drugs like had been used for specific diseases, and then they tried to see if they could be repurposed to treat other diseases that they hadn't been designed for. And so they built up this entire graph using how the molecules that form the drug are related to each other. And then they ran graph convolutional networks on those to try to predict things about the disease. So like interaction with the known proteins that had to do with that disease. And so they showed some really cool results where like drugs developed for like bipolar disorder ended up being useful for Crohn's disease, or drugs for the flu had been repurposed and were able to be done with used for psychotherapy. The kid was from Stanford. The guy, Yerleskovic, was the guy that presented the talk. So maybe we'll drop that in a link somewhere and be interested in that.
Zoo.
Yeah, I mean, these look to be like, this is a generalization of image processing, right? And we all talk about how amazing image processing is and how it can be applied to all these different things. Imagine how much you could do with like a general graph, like a general machine learning for graphs. I think that's really interesting.
All right, thank you.
Okay, so we are way early, but no, no problem. Yeah, that's true.
I'm perfectly on time.
I just saw Ian is back from dinner by the time he's like, what are we doing? That's okay. We'll think of something. Maybe we'll take a break.
Okay.
Cool.
Okay. Cool. All set? Sure. Great. Well, thank you for having us. I'm Jordan Bilich. I work at Remesh.
I'm Mike Varga. I also work for Remesh. We're both on the research team. We do data science and some fundamental, linguistics research. It's probably the most related field to what we did. To use a Remesh.
Yeah. So we're going to talk about learning to rank from pairwise comparisons, which is very central to what we do at Remesh. So first, just to get your heads in the right spaces, let's talk about what exactly that is that we do. Okay, so Remesh is a platform for engaging and understanding groups of people at scale. So that can be customers, clients, employees, political constituencies.
So when we say engage, we mean basically have a one-on-one conversation between a single person and a large group of people. A group of people can be as large as 1,000, be as small as 20, 25. It could be a team of people, or it could be a whole large sample, depending on what your use case is. Is it running right now?
What's that?
Is it up and running? Is this room part of it right now? Maybe at the end.
Yeah. You'll get a chance to see at the end. But for now, basically what happens, there's a moderator. The moderator asks a question, like, in general, what does insight mean to you? Sometimes it's a vague question. It could be very open-ended like that. It could be very concrete. Part of the novelty is that it is, we are able to work with very open-ended questions like this because participants are then given the opportunity to respond in a free response setting in this.
So there's also traditional polls where you can just say, here's the 4 answers. Pick from one of them.
Right.
But
So
this is where the more interesting.
This is the core, very cool thing. Okay, so the thing that allows us to do a lot of extra stuff with this data is that after they respond, they're then shown pairs of responses, and they're that came from other participants, and they pick response A over B, and this goes on for about 2 minutes. In general, that's the usual time period, and we usually get 6 to 10 votes per participant. And this is the result. We're able to rank the responses. This actually came from a conversation that we held internally at Remesh to sort of determine how should we
how should we display insights to our clients? So it's like basically we're trying to gain insight about insights.
Yeah, so this is a very meta conversation. But so the top definition that we had for an insight, according to our method of ranking things, is
According to the group.
according to the group. Thank you. Is a piece of discovered knowledge which you can use to take action. Some other popular ones were some previously unknown or unverified observation, an answer to a question, something that answers a question. And so one of the main components, other than so we get all this vote data, and that's a lot of data, but it's going to be impossible to distinguish between sometimes clearly here you have like two things that are very similar: answer to a question and something that answers a question. So one of the key things that we do is we deduplicate responses which are very similar, toss them together, and
we do this using a pretty well-known method, cosine similarity of the embeddings of the sentences. And so a lot of our ML goes into how do we produce the sentence embeddings for those sentences so we can cluster them, deduplicate them, and produce, as you can see, this reduction, similarity reduction, is up pretty high, and you have very, mostly different answers. If you were to knock this similarity down, we're not deduping as much on semantic similarity, and you'd have many more duplicate answers in here that mean essentially the same thing. And so basically, go to the next slide.
Sure. Okay, and so the question that we want to talk to you about is how do we do this, or how should one do this in general? Okay, so here's the problem. If there are n responses, then how many pairs are there? You have to, it's n choose 2. So that's n times n minus 1 over 2 possible comparisons. So we have an awful lot of comparisons that we could ask them. And in general, we have about 1 to 200 participants per conversation. And okay, so you might say, well, you don't have to ask all the pairwise comparisons, which we definitely don't, because we're looking at 20,000. We get 6 from each person, and we would need 20,000, right? So, okay, well, there are, if you want to be smart and be a computer scientist, you can say, well, wait, there's, quicksort or whatever it is. I have no idea. I didn't study computer science. That scales in, that says the worst case is big O n log n. But even so, that's still 460 votes per person, which is just totally out of the question. And well, right, typical voting period, we only get 6 votes. So what's the solution? Well, there are 2 things. One of them is to take advantage of the similarity of responses, and not just to do that. So currently, we're like what you just saw there. There's the taking advantage of that similarity of responses by at the end deduping and not showing as many responses. But ideally, and this is what we're going to talk to you about today, we'd like to be able to use the similarity to infer the way that people's opinions, infer opinions about different responses from those whatever features are similar about the responses. So that's one way, and we take advantage of that mostly using word embeddings, which we're going to talk about. And the other way is by taking advantage of the similarity of participants. And so you obviously, so if you have a large enough pool of people, you can get a coarse approximation to how popular a certain response is by just pooling everybody's votes together, right? So that gives you a coarse idea. But we would like something more granular. We'd like to be able to, for each individual person, find out a pretty good estimate of how they feel about the different topics that are being talked about in the conversation. And the way that we do this is with collaborative filtering. So we're going to talk a little bit about collaborative filtering. Okay. So word embeddings. You want to talk about word embeddings?
Yeah. So
Actually, I wrote this slide. Do you want me to talk about it?
I wrote the whole conversation.
No, I didn't. Okay, well, so word embeddings. The basic idea is to find a map from words. So the map, we'll call the map back, so that you can input a word, any English word or whatever language is in your scope here, into this function, and it spits out a vector in Rn, which in the embedding that we use is 300. So it spits out a list of 300 real numbers.
So what's Rn?
Rn is, thank you. Rn is a list of 300 real numbers, but Rn is 300-dimensional real Euclidean space. So in other words, it's the space of all possible lists of 300 real numbers. And so the thing that we want, the thing that we're going to enforce, and this is why machine learning models are so amazing, is because somehow I'm able to just say, well, we're just going to figure it out so that the probability, the log probability of word 2 and word 1 occurring near each other is given by the dot product of the two vectors. And the dot product, if you just to refresh your memory, is just you take the component-wise sum, the component-wise product of every entry in the vector and add those numbers all up. And so we just force our thing to learn that. We don't actually do these word embeddings, but it's just a neural network, and you say, oh, you're wrong, change. And you pass that back through over and over and over again. And finally, there are these beautiful word embeddings that okay, so here's the thing. They did, if you are teaching some vectors to represent the probability of words co-occurring, like there's actually a lot of knowledge that you need to encode in order to predict what two words are going to co-occur. So it turns out, somewhat surprisingly, that these models encode some non-trivial semantic information. For example, and these are like the classic examples, if you take the vector of king and the vector that corresponds to queen, and you subtract king minus queen, this is very close to the vector for man minus woman. So in some ways, vector subtraction seems to correspond to analogies. Another example is vector of Paris minus vector of France is very close to the vector of Madrid minus the vector of Spain. Amazing, right?
This actually works. We did it today.
Yeah, we did, and but like, we almost did an example for you guys that we're gonna let you do these analogies yourself, which you should do, but it just doesn't work that often exactly the way that you'd like it to. What was it? Soup is to spoon as steak is to silverware drawer, or something like that. Actually, that's pretty good if you think about it, because it's like for the soup, you just need a spoon. For the steak, you need all of the tools. Okay, and so we use these number batch word embeddings, which is they're trained as described with more complexity, because I just really glossed over that stuff. But additionally, they use the concept net knowledge graph to help encode additional semantic information. That's sort of like, they do the word embedding thing, and then with any leftover room to play, they use this graph of like concepts that basically already have those metaphors encoded to make the rest of the choices about how this space should be shaped. And so we're going to give you the opportunity to, first of all, here's if the embedding were two-dimensional, right? This is something like what you would expect to see. And I'm sure that nobody can read any of these words, because I barely can. But
so there's things like batteries and charger, tool saw,
DeWalt,
got light bulb, things that are similar that you'd expect to find related to each other semantically or
vanity,
in context.
sink, bathroom, bathtub, faucet, table, kitchen. Up here's refrigerator, oven, LG, microwave, GE. So as you can see, it embeds things of different types in the same like space, but things that are similar or like tend to be mentioned together end up together. Yeah. Okay.
So how many of you guys have your laptops?
Or a computer?
Or something. So
or I mean or your phone. Your phone
actually,
should work too.
I'm serving a local Django app that you can just play with the word embeddings and just search anything you want, and it'll pick the like 15 most similar things in the number batch word embeddings and show you the similarity with them and order them.
So for the purposes of the Hangout, I think is it okay for me to pull up your browser and go to this?
If you just do a new tab on this one.
Oh, do a new tab right here.
Oh, so your mouse right now is
Yeah.
on the.
It is capitalized.
It's on there.
Uh-huh.
So
This is different.
Yeah.
I see.
It's
So
just the hangout, which is.
I see.
showing, so
I
you can kinda
makes
see
sense.
it.
Got it.
It might be.
Yeah, we're not web developers either, so.
Yeah. So yeah, we are on the research team, and there's a good reason for that. Okay, so this demo uses the full number batch embedding dictionary. You can enter a single word, and you'll find some similar text. So anybody who doesn't have their phone but wants to play, give me a word.
A word or a sentence that you want to find some similar words to.
Everybody has their phone?
Probably gonna work right out.
What, computer?
I got the page not found.
Honestly, we probably have enough time where we can take a second. We want to like all get logged into Wi-Fi real quick.
Sure. Oh, that's a good idea. We should have mentioned that.
The Wi-Fi password is.
Computers. That's like a mattress and a
Yeah.
computer.
Yeah.
Oh, that's okay.
It's just a T and an H.
The T and the H and
Wait,
the
so-
loud vowel section.
Let's just type the password.
Oh, good idea. Type it where?
Tech High 2000.
Oh, the network is digital feed. And they're typing in the password. And that, right there.
If you can see that.
But your page,
There's also one back
Sure,
there.
he's on it.
my local. The page you wanted us to go to?
It's remesh, REMESH
8,000.
dot local
Yep, I'm there. I'm on a red board.
colon 8,000 slash embeddings.
This is not embedding together.
Are you stress testing now?
No, because it was, I changed your login to digital.
Yes.
Put it on. I don't know.
Alright.
Okay, guys, okay, so we'll just do it up here for you.
How many people can get to it?
Mine's saying
3 or 4.
server.com.
Ah, Mike, maybe you can only host so many people.
Yeah, I mean,
Okay, well, we can also probably make some of this available at another time, or you can come up and talk to us afterwards. So anybody else who wants to see a different list of things that are similar to computer, and definitely not Wi-Fi Tech High 2018? That's a good question. We have a character level embedding too, so Wi-Fi, WiMAX, HyperNet, wireless network, access point, USB modem, coffee culture.
and so these values are actually the cosine similarity are just like the normalized dot product between the vectors of the sentence or the word said and these words in the dictionary.
And I'm sure that you can probably, if you just do a Google search, you'll find another place where you can do the same thing. But this is just this is an example of how these things work. Yes.
What's your training purpose?
So we did not actually train these. They're trained on very, very, very large corpus of like basically all of Wikipedia, tons of web pages across the internet, Reuters. I mean, it's just huge. And like Google releases one too. We like this
There's a
one.
number of different sets of word embeddings. We found the numbers afterwards. He's agreed that's my best out right now.
Yeah. So I mean, you theoretically could train one of these yourself. It takes a lot of processing power to do though.
So yeah, I mean the classic ones like Love and Word Develop, right? But there are some known issues with that. In particular, they seem to be trained on biased data, which, as we've talked about in other sessions, leads to some pretty wonky behavior a lot of time. So there's one called ConceptNet, which is newer, came out of MIT Media Lab. I believe Number Batch is based on ConceptNet.
Yep.
It's an extension of that, but then
Aiming
also
to reduce the bias.
Yeah, so ConceptNet
yes,
is
with the aim of reducing the bias.
yeah, as I understand, ConceptNet is basically a semantic network. It's not actually a word embedding, but then they take all of that like information that's encoded in this like learned ontology that they also get from. I think they do it with they just have people contribute by like saying it's supposed to just encode common sense knowledge, like stuff like a bank is a place where you get money and like simple things
Is
like
it?
that. a bank is a place where you lose money.
And then you see a casino next.
Right. Yeah. Exactly. Well, no, but I mean that's I think that the inspiration for that was that it tended these word to back and stuff tended to encode metaphorical information like that. And so they thought, okay, hey, we can sharpen this and reduce some bias by like explicitly taking a learned ontology and then, sort of changing the word embeddings. That's really fancy stuff that I don't know the details of.
We also did PCA on this whole set of embeddings, and actually, like the principal components correspond to things that are almost too almost like fixed, like they decided kind of
Yes.
the space at the fundamental.
It tells if you look at the
So,
most similar words to each principal component of the like space of, it tells a little story. It's like a joke.
I think
Do-
you got a question.
Sorry.
Oh, you know how they're-
Oh, no idea.
No idea.
Like you have like single words, and I was like,
Right. Okay. So they do something like that to. I think that there's a pretty like relatively straightforward statistical test that you can do to find out. Okay, these three things are occurring way more frequently than you would expect them to in any situation, and so we're going to treat these as a token. I don't know exactly how they do that, but I think it's very, very important to do that actually because there's not a straightforward way of combining Montreal and Canadians to like get a baseball team, right? Unless you put some wacky stuff into the vectors for Montreal.
Yeah, exactly.
Like baseball.
So can you type in
Like baseball, right?
the word in there?
Yes. Which word?
Oh, I don't know. I don't know. Fire.
Fire.
See the fire thing, sure.
Unfireable. They're really good. Suppressive fire, cook fire, supporting fire, close.
DC fire. That's actually really, it's really interesting that they all are like 2 grams that end with fire.
So just for the sake of time, I want to move on forward. We have time. Okay. Any other requests for words? What?
I have a question.
Yeah. Oh, a question.
I was gonna ask like what else do you use I guess to like make the similarity of phrases.
Yeah.
You clearly can't just use.
Oh, you mean for like for if you have a sentence, right? Because we get these phrases.
So what we do is we tokenize a sentence, remove some stop words, we have an embedding from this number batch dictionary for each word, and then we use the Aurora Liang Ma, which is actually a model of combining them using some method.
It's pretty straightforward. It's basically like
it normalizes it and then combines
it normalizes it. It takes out like due to repeated frequency of word. It doesn't. If you have the same word twice, it doesn't allow that to like really compute to fire or something. You know, just because you said fire twice.
Jordan, if you click on, there's a link on this page
Yeah.
to that paper.
Yeah. So there.
Simple model. Yeah.
Simple model that is Aurora Lang, and basically, you want me to click on it?
Yeah.
It's basically like.
So it's
Just click on
this
that.
exact
It's a
paper.
Mac thing, just click on it.
Oh, okay. Oh, I force touched.
Yep.
Ugh.
So yeah, you can look this paper up and implement it.
It's basically like for the accuracy that you get on like sentence length, sentence level embeddings from more complex models, the accuracy gain is just like not worth it. This is pretty well recognized as the best way to combine word embeddings to get a sentence like for the level of simplicity.
Yeah, and you get an embedding in the same space. You
For
can
now.
compare it to a single word or another sentence.
I mean, yeah, that's probably I'm not.
And so that is actually the method you use when you showed an example of the deduping of the responses on the remesh platform. That's the embedding method that we use. Essentially, all the responses get an embedding through this, and then you can use the similarity to dedupe.
Okay, so I'm gonna go back to these slideshows. Is that okay? Okay.
You guys work in any languages other than
Currently, no. We actually translate to English, do the similarities, do the algorithm, and then translate. Well, then just give the response.
The problem is that there are not really good. There are not word embeddings that are as good in other languages, unfortunately.
Yeah.
I think that'll change soon.
Yeah, I think it's a matter of time, honestly.
Google Translate's getting a lot of data. There's a lot of work going on.
Right.
There's also, because we just talked about graph neural networks, there's also a neural network-based approach to embeddings called ELMO, which is embeddings from language modeling. The idea is you build like your deep LSTM, like your deep network, and then you try to predict the next word. And
Or the previous.
What?
Or the previous.
Well, yeah, I mean, you can use it bidirectionally, so you could actually do, well, no, it's usually the next word actually.
For language,
yeah,
for those ones
in
specifically.
particular.
But for like, I think this is like basically just tries to predict nearby words. Yeah.
Right, but I'm saying for this in particular technique, learning to predict the next word with the deep model
The last layer before you actually predict the next word is a really good embedding to use for this kind of stuff. So,
and it's for that same reason again that like you had to, in order to predict the next word well, you have to learn something pretty meaningful. So. Okay, moving on. Okay, so collaborative filtering. So the basic idea here is to embed items and people in a relatively low dimensional space. And I say relatively because sometimes the dimension of the space is you know, the space of all movies. That's like the primary use that I have seen of this. And so like a one-hot encoding of all movies is like 100,000 dimensional set. So what we're talking about, relatively low dimensional space, like 30 dimensions, in which, so that people are close to items that they have, that they value, items that they have, you know, high utility for. So more precisely, you want to find embeddings so that if Zi is, well, in our case, if Zi is the vector corresponding to person I, and Wj is the vector corresponding to item j, then the utility of item j to person I is the dot product Zi dot Wj. It's very, you know, it's
Very much like a similarity.
very much like the word embeddings, and there's good reason for that. It's just that, you know, linearity is such an easy thing to deal with. It's kind of the way that we think at the highest level of PQ. So the typical setting is that you get noisy measurements of this dot product directly. Like it's, you know, on Netflix, you have a 5-star scale that you can rate movies on, and we take as a measurement Zi, like, okay, they ranked at 3 stars. That means that Zi.wj, after some kind of whatever the appropriate psychological transformation from stars to real numbers is for utility, then we take that as, you know, the word that this is what Zi.wj is, and then we try to fit vectors Zi and wj so that all of those, so that everybody's rating is satisfied well. And this actually, it ends up being, it's a stretch to see it. I didn't get it at first, but it ends up being basically taking the matrix of ratings and doing the singular value decomposition on it and taking the top 30 vectors. Yeah, and that's really well described in this paper by Salakudinov and Min for Netflix's collaborative filtering system, or at least the one that won the Netflix prize for something like this. So what we get is noisy measurements of which one of these two options is better, right? So we get we get something like noisy measurements of the argmax of Zi.wj. This is the thought A, and this is the Zi.wk is thought K. That somebody else is, we're voting on other people's responses, so we get some kind of noisy measurement. And we had to adapt the collaborative filtering system. And we model this with a random utility model that is pretty well described. He invented it, McFadden, or he or she, in 1973. And basically, we model the probability that I chooses j over k, conditioned on these vectors Zi, Wj, and Wk. So like, if you know these vectors, then this model asserts that the probability of choosing Wj over Wk is Zi.wj minus Wk. That's just we're sort of modeling the utility Zi.wj. That's the utility of thought j to person I. And this is the utility of thought k to person I. So this is just the difference in utility. And we apply a sigmoid function so that basically, if the utility is really low, there's 0% chance that they're going to make the wrong choice. If there's a big difference in utility, there's no chance that they're going to choose j over k. But if there's a very, very, very big difference in utility, like that j is way better, they definitely choose. So that's what this sigmoid function looks like. It's a logistic function, the smooth S shape that many of you are probably familiar with. Any questions there? And so the question is, how do we fit this just perform maximum likelihood estimation, and it's relatively straightforward. The trickiness that we do, it has more to do with how to do it at scale.
So for maximum likelihood estimation, that means you have labels as to like what the person actually choose.
Yeah, right. So that's what we collect. We have this vote data. We have a collection of choices which we assume are independent. So we get this big product of sigmoids. This sigmoid of zi dot wj minus wk, sigmoid of zl dot wm minus wn, and so you get this huge product of that, and we just maximize the log likelihood. So basically, it's a product of a bunch of these functions, but that's easy to take. It's not easy to maximize that with calculus. It's easy to maximize if you just take logs, and you get a sum of log of this sigmoid, log of that sigmoid, log of that sigmoid. You just take the gradient with respect to every variable, and then you change all of your parameters in the direction that they need to go to make the model most likely.
Yeah. So they could minimize log likelihood?
Minimize negative log likelihood.
Oh, yeah, sorry.
Or maximize the, yeah, I mean, either way you look at it. Okay, so we're going to present a hybrid method today that we're going to ask you we will ask and answer the question for you. All you have to do is vote, and we'll fix the vectors. What we're going to do is fix the vectors as their word embeddings and just fit on a single user basis. The more correct procedure here is really to assume that there's some kind of map from the feature space. So the analog, instead of like saying the one end of the spectrum here is you know nothing about the thoughts, you know nothing about the items, nothing about the users, and you fit it using maximum likelihood estimation. The other thing that you can do is say, we know these features of the items, we know these features of the users, and now we're going to fit matrices that map these that just linear maps from the feature spaces so that the dot products do what we want them to. And that is a more appropriate thing to do, but it is, we wrote this in one day to show you. So, and so what does this look like? Before we actually have you do that, I want to show you more visually. So we have some vectors, wj. These are the blue things. Let's say that these are the word embeddings of some words that we want you to vote on. Then if this is wj and this is wk, then this red vector is wj minus wk.
So essentially, if you make the choice that you like this thought here over this thought here, what we learn that wi minus wj is this vector here, and then you have your own vector that if you were to take this and dot it onto it, we should be able to know that you picked this way, or if you made the opposite choice, the vector would be the other way, right? The sigmoid on the z dot this vector tells us which one you're going to pick, right? And that those are the things you learn by getting a bunch of these examples.
And here are the set of all of the wj's minus wk.
So you take the local sigmoid of all options?
Of all of the options that we have observed people making choices on. So right here, these are the vectors for all the options, just for so that you can see what that, like these are all basically, if you're sitting on our end and you're thinking, how are we going to choose pairs for people? These are the options that we have. And if we were making decisions, if we were saying people never make errors, then observing that they liked wj minus, that they chose wj over wk, that would mean that they would have to lie in this. They would have to lie in this half space. We would insist that they lie in that half space, but that's a stupid thing because people make errors. So yeah, go to the next slide. Okay, so this is like the likelihood function, and this is what it looks like when we know nothing. In reality, we actually do regularization. So for anybody who's concerned about that, like this really should be basically a very broad Gaussian right now. But after observing just this wj minus wk, this red vector you should think of as the difference between two feature vectors. We observed that they chose this. So that means that we have high likelihood here. Yellow is high likelihood. Purple is low likelihood. And so, and white is the unknown z vector. So I generated some data. What I did here is I generated some data, and now we're going to try to we're going to try to find the white vector. Okay, so this is after observing one choice. And now we should observe another choice. And notice that we've now chopped off this part of the space. I think these vectors are not coming from the right place.
The Z is right. The white one's correct.
Yeah, the red one is offset by one slide or something like that. So,
But basically,
in any case, each time we're smoothly chopping off half of this space. Okay. Again, smoothly chopping off this, smoothly chopping off that, and just keep it going. And eventually you can see that we converge to something that's pretty close to at least the correct direction. We're like very sure, and the reason that it's not actually on this vector is because I generated with maximum likelihood estimation and no Gaussian prior to constrain us. So basically, it's always, as long as, we could always make this model more likely by insisting that the Z vector goes way, 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 way out to infinity. So
you'd have to use L1.
you have to use some regularization to get in the,
so
it doesn't go out to infinity. But that is, you know, this is the actual vector, and we would estimate it to be something that's in the yellow area. So what you can see is we got the correct direction, but that's really all that matters in terms of like predicting what choices. I mean, that predicts. That's mostly what matters in terms of predicting choices, if you think about it, because
you're going to normalize the vectors when you do the cosine similarity.
Well, for predicting their like, but also just like for predicting what choices they're going to make, being close to 0 just means that they're voting pretty randomly because you have the dot product of everything being 0, and that gives you a sigmoid of 0 is 0.5. So basically, this direction, the thing here is direction is the most important thing. So any questions about what I showed here? I know I'm kind of rushing through this. I just don't want to not get to the fun part.
All right, so we have another one of those local like demos for those of you that want to try it out. Basically, it's just, well, we can bring it up.
Yeah, so can anybody get to remesh.local:8000/vote?
So basically what we've done here is
What do I like?
Yeah, I know.
it works on some. My computer's probably just saying.
Phones they shop.
Yeah.
/vote, yeah.
Can you get it?
You have an iPhone? I don't know.
This is a Samsung. Just from the phone.
Are you on the Wi-Fi?
Yeah.
Are you on the Wi-Fi?
Yes, I'm on the Wi-Fi. You're on it.
Okay.
All right. So we can do it here.
Okay. So the idea is basically just it's very primitive. This is not remesh. This is not what remesh looks like. You'll see remesh and stuff. We just have to save face here. But this is a very primitive version of remesh. We provided the options, as I said. So we just provided a bunch of cuisines. And then what we're going to do at the end is we're predicting your participant vector in a space, a semantic space. So what we're going to do at the end is re-infer. We're going to find a vector that represents you in semantic space, and we've restricted the things you're going to vote on to be cuisines, and then the options that we're going to predict are dishes. So this is the little twist on it is that from voting on a bunch of different cuisines, we're going to tell you what you should eat for dinner. So can I have a volunteer so that since we can't all get on it, can I have a volunteer to be the person who tells me what thing they like more?
Sure, I will.
Great.
Yeah. Really interesting.
Okay.
Okay.
No, say the thing.
Cajun food.
Cajun food.
Vietnamese. Mexican. French. Belgian.
So we set it up so you have to make 10 choices before we actually show a recommendation.
Thai. Cambodian. Asian. Thai.
All right, so there are.
Oh, there we go. Chicken noodle soup. Chicken noodle soup, frozen yogurt, butter chicken, pizza, fried chicken, Cuban sandwich, I'd say that's pretty accurate given the way she voted, guys. Here, and now let's see how it changes with the next vote. So, Sichuan, lo mein, chicken and waffles, turtle soup. Okay, Thai food.
Thai, spring roll.
Lebanese or Cantonese?
Coming up.
What's with the chicken noodle soup?
I don't know.
Chicken noodle soup and butter chicken. By the way, we work for Kraft. Okay, so now something that everybody definitely will be able to participate in is we're gonna just run a regular remesh session with one. We'll just ask one question, and I'll leave it up to you to ask the question to the group. So we'll pull it up, or if you don't want to, I can ask one for you.
So this works well on your phone.
Yeah, I need to. Well, actually, I just need to. We'll have Charlie type it from his computer probably, because he has to be logged in as this.
Yeah.
So,
Okay, so now,
this one that says platform demo.
so you can go to this link, remesh.chat/YLWB. And this is moment.
Is are you up?
That's way L.
So I just said, welcome to the ML meetup.
Are you guys?
Yeah.
Everybody's. Anybody who's on wants to be on, or? Okay. Yeah, we'll give it a second. You can always ask the old, "Are we ready, Mike?"
Yeah, I was about to. Are we allowed to text here? Or is it on?
He's gonna ask the question, and then you'll be able to respond, and then you'll vote on the responses.
Looks like Chrome on mobile works.
Chrome on mobile works.
Firefox.
Well, I mean, this definitely, this definitely works. This is the thing that we were showing you here, is something that Mike and I did in the past couple days. So,
Are we ready?
are we ready?
So yeah, I'm just asking a really simple poll question to start with. So, but the big thing is we can ask an open-ended question, and you guys are going to need to vote on each other's, so we can get a ranking from you guys about the thoughts that you all said, and they're all responses to an open-ended question. So, what do you want to ask the group?
I was thinking something along the lines of like,
What do you?
what challenges do you foresee, or what things do you foresee being important for ML, or what do you want to do for the next meetup, or something like that? I don't know.
Sure, yeah. What do you find most challenging about learning machine learning?
So I'm going to give you guys 2.5 minutes to answer and vote. What do you say? What do you find about?
What do you find hard about learning machine learning? Most difficult?
Learning machine learning. Now you guys can enter your responses, and as soon as you go in, you can start voting. You can actually go back and keep entering more responses. But
It's so cute.
that is the worst thing in the world.
I'm seeing a trend already.
Am I supposed to just continue voting?
Yeah.
Or enter a new response.
I mean, the more you vote, the easier my job is. So.
I mean, yeah, it's just like.
It's so good. What happens when you answer something with a question and you're answering a question? I thought,
Hey, everything's fair game.
Yeah, I mean, you can put in whatever you want. We always put into our own
was
Paul's dog next year. Funny.
Yeah, on a first one. Yep.
That's why I just don't profession stuff.
I prefer not to like my arrests.
Anyway,
Right, so you can see like a lot of the responses kind of mean the same thing, written differently.
That's
And
what
when
we do.
you're choosing them, you know, you're gonna preference the thing. But disagree with. And actually, once we hit the halfway mark of the thing, we start actually dropping the most unpopular things and only doing the pair choosing through, like, from the popular set essentially, so that we can actually be more confident about our calculations on the things that are more popular.
Why do you hide the other two options?
Hide the other two?
I can't decide, you gotta click the I can't decide.
Oh,
The same and just like.
that's actually a current debate. We want to make those much easier to use because we actually want to get those signals.
Yeah, it's a lot more fidelity in the data.
Right. I think so. I think that the initial, this is my guess at the initial reason because I wasn't there when this was, that was made the way it is. But my guess is that they were worried that people would just click I can't decide all the time, and they wanted to get more data. But it's definitely something that we want to open up and see whether.
Can we get to? Do you have it up? It's done.
It's done. It's on. You should have the. Oh, you want me to pull
I
it
want
up
to put
here?
it on the screen.
Yeah. I have to go to the participant link, I guess.
You'd have to.
Just stop sharing for a second.
Well, no, don't stop sharing.
Oh, I just have to.
Oh, well, you can actually.
Yeah, sure. Just put it in.
What is it? YLWB?
Capital Y. Capital Y. Yeah. All right.
Yeah, same.
Can I scroll down?
We can't.
Oh, I see. I'm on the. I just didn't understand. It's hard to.
Yeah,
I can't see the person. There it is.
You can also kind of.
You can see it on
swag.
here.
Yeah.
You can see it on here. Mike.
All right. So here's all the responses, right?
Get data structured. That is so true, right? Or software libraries.
We actually need we need not to participate. But anyway, yeah. So
What do you mean?
because you can't do anything with this.
Oh, yeah. Well, you're gonna have to log in.
All right, so you guys get the idea, right? And so we showed you earlier, this is the participant link one. You can see the top four. If you were the moderator, you want to ask me a question, you'd be able to deduplicate all of these with the similarity between them, which I really want to show you. That's the whole point, right?
I can help out.
You do.
Move it over to. I'm not. Depends on.
So
So you can't type it into this computer, right? You need to-
no, I can. Yeah,
You
I can.
So those are the top
Okay.
four.
So, but what do you need in order to be able to do that?
Just type it. Just type in this link.
Well, right. So what
Most
is the
popular?
popularity out of?
Why?
That's something also that we have a lot of complaints about. That we're in the process of changing is to kind of more meaningful
Slash.
popularity score.
2
My argument-
capital Y,
my-
capital
my-
W 5.
My preference would, but this is
Cool.
probably skewed because I'm first of all, I'm
Oh
a
my
but also
God.
like
Oh, it's
that
because
kind of
it's
minded
you.
person. I think that we should say that explicitly something like
I won't be able to remember my login
is,
off the top of my head.
the
So you need
probability that a
to-
randomly
Yeah, can we just?
selected
You want to
person
switch
from the
this real
group
quick, so you can turn on?
would
That's actually.
pick this response as the top response. I think that that's a very clear, distinct thing to say.
Yeah.
But what you end up with is all the popularity scores would be like 0.05, 0.1. Like highest popularity being 0.15 is not impressive to people. So most of the fact that it's on a scale of 0 to 100, I think that decision was made to make it more appealing to a non-technical user. But I think that we have some kind of debate about what the best way to, in general, represent all of our output. Because actually what we have right now is we actually are learning a lot more than just popularity and consensus, and we're trying to figure out how to present that information.
And the super nice thing is we would now be able to dig into why you think get data structure is the hard thing, right? Like the advantage over a typical survey is you have to write your questions and then send it out. Right. But now we would be able to dig into that particular issue right now with you and get
Just
very
say,
high grade.
you could just ask another question
Exactly.
about
Just ask another
that.
question about what's hard about getting your data structured.
Do you guys do any sort of like K-means or anything on the participants to try to figure out, like, we've got two distinct groups of people?
Yeah, we do.
Versus liberal or whatever.
Yeah, so I mean
We call it attitudinal clustering, and yeah, you take basically that vote matrix. Some user picks some thought, and you do clustering on those votes, and you can say 2, 3, however many, and you can basically cluster the users into groups that voted similarly.
Yeah, and there's also a at the beginning of the conversation, you would usually be asked to input some demographic information if it's like for market research or if it's for even if it's for employee engagement or something like that, like what team are you on? And then we have various, cross, who's saying this. You can look at just the popularity for a certain group. You can restrict your attention to this.
You do all kinds of things.
Yeah. So there's like an analysis panel that you can pull up after this that has more information.
Does remesh have paying customers?
Yes.
I'm assuming those paying customers use focus groups before.
Yeah.
Do they remark as to what kind of they get versus focus groups?
Yeah, so I don't myself interface with the clients often, but it's, from what I've heard, my understanding is more personalized, open-ended responses and more understanding of how those responses relate to the group, rather than having to dig through 100,000 surveys or 1,000 surveys and try to figure out attitudes that are the same. You can kind of you can get that information right off the bat by splitting this by demographic information or by any of the filters that we offer. So it's easier to find the thoughts that are representative of a group than just sampling the thoughts, because you can find the thought that's most popular to that group.
Yeah,
that's kind of very representative.
One of our biggest customers is Procter & Gamble, and they were for a long time doing their market research in-house, and then like in the 70s they switched it to outsourcing it to other companies, and just recently they've started to shift back toward having their research done in a more qualitative way, but they still have to balance it with quantitativeness, and so they found us at the right time. So they're one of our big customers. We also, Unilever and Coca-Cola are big customers. So
I would also say that the scale of the data, a focus group is small, and to be able to get the granularity that you want, you can't have a lot of people, but you can still get that granularity at scale. And so we kind of figured out the more people you have, the number of unique ideas doesn't increase linearly, right? It's like,
the unique ideas starts to level off, and you really feel like you're.
But there is a peak where, like, if you have 250 people, you get pretty much all the unique ideas from that about that question, right? So that's the stuff you can't get from a focus group. You're not sure if you're getting all the unique ideas or the most popular.
Yeah, I think a typical workflow in market research at least was do a focus group, get the idea of what question you want to ask and what options you want for your quantitative survey, send that out, and then wait, and then get it back, and then analyze that data. And so that's basically a 3-week process that now is 2 minutes.
It's also probably more costly, I would imagine, too.
Absolutely, way more costly. I mean, that's the main thing. It's cheaper. It's cheaper and it's faster.
Cheaper, faster. Yeah.
Any other questions?
When you were building this stuff initially, how did you get people to take surveys?
So I've been with the company since January, and he's been with the company since August.
So Charlie?
Charlie has been with the company for longer.
Yeah, I have a great answer to that, but basically we hired some salespeople a few years ago and sort of began the very slow process of trying to get into the market. And after several years of that, we managed to get some actual clients.
Yeah. Which we are expanding very rapidly right now. We don't have a posted job in machine learning,
but we're growing, and there will be some.
We're always open to the right person at the right time. So anybody who's interested in that,
There's a research
Touch
team,
base.
there's just a development team. Development team is really focused on obviously scaling, right? Because we are aiming to do, so right now we limit our ML and our NLP at 300 users, because you got to do a lot of clustering and a lot of stuff. We're aiming to be able to do like 10,000 soon. So like that's a pretty big engineering scaling challenge. So to the general developer, if you're interested. What's your question? Charlie?
Our back end is written in Elixir. Our front end is currently on Angular, but we're migrating to React. So that's about half done right now.
All the MLs in a Python app that communicates through RabbitMQ to the back end.
Yeah, and we're serving everything through Kubernetes.
Yeah.
Nice. How much are you doing in Cleveland?
3 months.
1, 2, 3. But this is the research team. This is the research team, and then there's one other person in New York who is.
And we work upstairs here.
Yeah, and we work in this building upstairs. So come visit.
Yeah.
So, oh, sorry. So to kind of touch on the question about focus groups, one thing that you guys remove is like dominant voices, right? So like small groups, like there can be like one or two people that kind of control the conversation.
Great point.
Those people are typically removed, because like they'll control other people, they'll influence other people's results. One thing that I found when I was doing this was lack of time was somewhat representative of me, but like nothing else was. So I was able to throw in 30 votes because it's no, this, or it's only one answer. So, but aside from that, so like when you're suggesting different responses, like yours is parametric, right? That's parametric control. So you guys have you guys ever thought of
To show the pairs?
Yeah.
So there's a couple things that we randomly choose.
Well, so like, have you guys ever thought of taking like a non-parametric approach to that, like applying like a Dirichlet distribution or something like that, to where like you're basically
To how to choose pairs.
Yeah, right. So like
So it depends on like what are you trying to do by like what do you want to accomplish by picking the pair that you're picking? So like what?
Yeah.
Right. So what are you suggesting be the thing you try to optimize?
So like you'd be optimizing on like where like probability mass is going to lie, right? So then you can better predict on like
right. And
you're saying basically like you're saying assume that your participants are drawn from like a Dirichlet mixture of Gaussian,
Yeah.
something like that.
Yeah.
So I looked into that a lot.
Okay.
And I couldn't do it. I mean, no, I couldn't do it and make it still be like and make it valuable to the company, basically. You know what I'm saying? Like that's I was convinced that that was the right thing to do, but it's very difficult to fit non-parametric models. It's very difficult to fit mixture models and find local maxima with mixture models. So, but I think it's a great idea. It's just a question of like how much is that actually going to add to. And my hypothesis is that we do a pretty good job at just with heuristics picking good pairs.
Yeah.
No, but we're definitely going to like try to optimize that in the future.
So other challenges you have to be training online.
Yeah.
As the choices come in, and then use the model that as it's training to feed back out and say what choices should we have. So for this user, so that we can identify where they are, and that's just a hard challenge too. Getting out there.
It's a very good idea though. Definitely a good idea.
So when you do this, and you have to pick, for example, those pairs, you have to balance between exploration and exploitation. Like the thing you think is the next best answer.
Yeah, we
well, right. It's like either any way you look at it, you can ask them. You can ask them. So they've got all their probability mass over here. You think, oh, it'll be really easy to squeeze it to the middle if we'll just get them to answer this. But the thing is, they're probably going to answer that because that's what you think.
That's just how it
that's your best guess. So you have to.
We ask a random pair. We pick a random pair every so often to put some noise.
And actually, the idea of like a reinforcement learning model for pair choosing is a current topic of discussion. Yeah, like for bandit. It's a bandit problem. So.
Very cool.
Okay.
Very cool. Any other questions, real quick? We have another couple minutes.
Are you guys doing any research on the data exploration for the customer end or data understanding type stuff?
So trying to figure out what our customers really want with this data and how to display it to them.
No, how to display it. So
we have another entirely analytics app that we're currently developing. That's not in production, not available, and it'll be hopefully out sometime soon. We have one and nobody uses it, so we're redoing it.
Cool. Thanks, Jeff. Very cool stuff. I think we're gonna switch to Ian at some point. Let me double check. I got a message in. Make sure he's online still.
Oh, I'm here. Can you hear me?
Oh, he's here.
The voice from the sky. I always wanted to be that person.
You're on the screen now. It's just your face, the Google Hangout thing.
Okay, cool.
But so I guess I'll introduce you real quick a little bit, and you can, or unless you have a slide.
No, I'm good to go. Go for it. Give me an introduction. I like to see what people say about me.
What?
Go for the introduction.
Okay. Cool. I'm gonna check to see if we can turn up the volume for you.
Okay.
A little bit. Oh, I think. All right, can we try that?
Hey.
Ooh, a little too much. Try it again.
Deep booming voice. I don't know.
Is that good, everyone?
Yeah.
Yeah. Cool.
Awesome. Awesome. Do you want me? You want me to jump in? Do you want to give me an intro?
Sure, yeah, I'll introduce you real quick. So this is Ian Livingstone. He's in Halifax, Canada right now, in Nova Scotia. He is the co-founder of Dropout Labs, which is where I work and do research and all that stuff. He thinks a lot about products and about products in relation to AI. He's worked with some pretty cool companies before, and he thinks a lot about this stuff right now. So I figured it'd be good to get someone like him in here to talk talk about the side that we don't normally see, which is how you apply this stuff and deploy it and all that. We talk a lot about research, but we don't get to talk about some of the like more traditional developer activities and how that's impacted by this new machine learning work. So, is that good?
That was perfect. I couldn't ask for better.
Right.
Awesome. So yeah, I'm going to talk a little bit about models as a product. Something I've been thinking a lot about since I started diving into AI, which is actually for me only 8 months ago or something. I met Jason through the OpenMined community. Is open models and ecosystems enabling developers to pick up models and build smart applications. And so this talk's pretty much focused on that. I threw it together pretty quickly. But before we dive into it, I'll give, Jason did a pretty good overview. I'll give a small overview of myself. I guess I like the double introduction. So as he said, my name is Ian Livingstone. You can find me on Twitter at Ian Livingstone. I've been co-founding startups for a while. I've been really focused in the last 8 years, or actually I'd say more like 5 years, on developer productivity. So building applications, infrastructure components, products that developers use to be more productive, to build better applications. And now working and co-founded Dropout Labs with a couple other people, which is super focused on building infrastructure to make it possible for us to build models that weren't possible for by enabling data scientists to take advantage of encrypted machine learning. So an example of that would be we want to have a skin cancer model, but medical data, we don't want to leak it beyond the confines of a clinic. So now with our technology, you could predict upon a model with the actual picture of the mole or whatever the actual component is of the skin ever actually being known to the model holder, the person actually running the prediction. So that's what we're working on. And if you want to learn more or interested in what we're doing, we have just thrown up a very, very limited business card style website at dropoutlabs.com. Cool. So models. Yeah, so as I was saying, I've spent a lot of time thinking about open source. I spent a lot of time thinking about developers, but one of the things that I've come across, and I'm sure we're all aware of, is that this stuff is pretty early on. And what I really want to talk about today is how amazing open source plus data science is. It's the reason we are here today. All of our best tools like TensorFlow and PyTorch are open source. But what about the actual models themselves? But before we dive into that, I wanted to quickly run through some numbers. I'm more of I used to be a developer. I'm not one anymore. I'm now like that haha business guy. Unfortunately, that's where you end up if you keep working on something long enough, if that's where you want to go. So 1 million. That's the number of Kaggle users in 2017, which is a really great proxy for understanding the number of data scientists and researchers that are generally active today. And interestingly enough, most of those are employed somewhere in the Fortune 500. So if you were to look at where most active data scientists and researchers work, there's some in startups, but it's a very small component. Most are employed by the Facebooks, the Googles, and the big banks of the world. So there's this huge dispersion between like where people actually work, and it's mostly in the Fortune 500. 25 million and growing. That's the number of software developers that are in the world. And most of these have no background in machine learning at all. It's very much a new form of literacy, much like code was. Machine learning, statistics, these are new languages, these are new things we have to learn, and a lot of them don't understand them. I know I didn't, even coming from like an ML background through school. And most of them work outside of the big technology companies. So most of these people don't work in a technology company. Most developers work in e-commerce. So they work for like, the Fairmounts of the world, or they work for the Salesforces of the world, people that are building applications that businesses use or that we use as consumers. But those wouldn't be considered traditional like technology companies. So to put some numbers in perspective for here, the growth rate of the number of research papers is absolutely astronomical. That's a nice graph up and to the right. That's what you always want to see. Currently, about 17,000 papers a year are produced related to machine learning. It's a lot of new knowledge coming down, a lot of research getting done. Not all of it's great, but a lot of it is good. A lot of it's pushing us forward, which is why like one of the top answers before was just keeping up with the field, right? There's about $3 billion a year invested in AI startups. And that is like, look at that nice exponential, that nice growth curve there up and to the right. You can see around 2010, it just sort of 2012, it really took the right-hand turn. And so that means there's a lot of interest pouring in. There's a lot of new money and a lot of new tools being built. And the reason for that is that right now, the estimate for the growth of the market for like AI tools or AI applications, specifically enterprise, so this is selling products to other companies, is to be $31 billion in 2025. And to back that up, that's a 53% year-over-year growth, compounding annual growth rate for the market as a whole. And that's just absolutely astronomical. So if in all other parlance, like in all other measures, it's the best data I could find in a short period of time. This thing is growing. AI applications are growing. Interest is growing. There's money flowing in. There's actual research getting done. And there's a ton of interest. What it really means is that, like the thing that we've been talking about, the thing that we all come to these meetups to talk about is like it's actually happening. And what this actually means is, in the next 5 years, as consumers, us sitting in the room or our parents or our friends who are not technical, or businesses are not technical, we're all going to expect that our applications need to have a layer of intelligence, that they're intuitive, that they're smart, they expect what we're about to do. They expect what we want to do. They can intuit what we want to do. And they just make our lives easier. They make our jobs easier. They make us more productive. But there's a problem. And the problem is that, as I said earlier, these developers don't have the skill set to add these applications to their apps. They just don't. Like we don't today. There's a huge gap in literacy. And we don't necessarily have the tools or the ways to create the literacy we need and the time to actually fulfill those, to see these estimates be true. And I love this comic. I love Dilbert, so I love adding a Dilbert comic when I can too. So developers will need to add intelligence to their apps because their pointy-haired here boss is going to come to them and say, hey, listen, our competitors just added some NLP feature. Our competitors just added this vision feature. Like we're getting crushed in the market. We can't compete. You got to make our application smart, and they're just going to get super frustrated. And so the first thing they'll do is when someone comes in and asks them to add some level of intelligence, to add a model, some form of AI cap, the first thing a developer will do is be like, well, there must just be a library for doing that, right? Like that just seems easy. I should like npm install it or pip install or use gem to install some library. And what they expect they'll be able to do is just go and say, hey, I'm going to include this little prediction thing for predicting my credit score into my app. I'll tie it up to some HTTP endpoint. I'll ask to predict on some data, pass it some inputs, and boom, I've got a credit score. Simple, easy, no problem. But the truth is they'll end up on a model zoo and basically be left to their own device to figure out how the hell to get this stuff to work and where to go. And so the problem really, so there's a couple of problems here, right? Like one is that unlike software development today, models are not discoverable. You know, they're spread out across various different zoos for various different ecosystems. They lack information, the quality of the model. Like a lot of the time you go to a model zoo, like I have no idea what the accuracy of this model is. I can't even tell like model A versus model B versus model C. I have no idea where to get started. Like it's unsure of who actually owns the model or the license to score sourced under. Like if you go to an open source project today, like if you mentioned Angular before, like there's very clear what the license are. It's very clear who owns it. It's very clear who's updating those things. And it's unsure of how to extend them for their use cases. So there are a couple of models that are very popular that actually have great documentation, but it's very unclear in a large breadth, the long tail of like the model market, or the model ecosystem, if you will. Like how do I extend these things for my use cases? How do I leverage this model and then do some transfer learning onto it so I get better results from my specific use case? And at the end of the day, like more than discoverable, like the biggest issue is that models just aren't consumable. Like the documentation is generally, if there is documentation, it's generally focused on training or reproduction of results instead of usage. Like how do I take this thing and actually use it in something? There tends to be no interoperability between frameworks and platforms. Like if I train a model in PyTorch, it doesn't mean I'm going to get the same results in TensorFlow. And doesn't mean it's even easy to get a model that's trained in PyTorch to run in TensorFlow serving or vice versa, or use Cafe2 serving and all these different platforms. You know, it's not clear what code and how to sanitize input data and how to massage input data and actually like give the model the input and interpret the output. Like that's not documented, and there isn't generally code packaged with that language independent that I can use for my Ruby app to then run in my inside my like from the Python app. And the thing that I've noticed in talking to software developers and talking to firms, even in the Fortune 500 that have like tried to deploy these things, is that it's super unclear how to actually deploy and maintain models that have been deployed in production. Like it seems to be just this dark art that everyone just has figured out. And so at the end of the day, what kind of happens is that like developers end up very frustrated and trying to deploy these things, or trying to get involved in AI and trying to get involved in trying to add intelligence to an app is like a very frustrating experience. And this means that they end up doing a couple of things, right? They end up going to like one of the big vendors like Google, Amazon, or Microsoft, and they pay for an AI SaaS service. So they pay someone and say, hey, you can have my data. I don't care what you do with it. I just want a result. I want to add some intelligence. A lot of them pack up another section will just pack up their bags and leave to say, hey, this stuff isn't ready. We're not there yet. This isn't prime time. This isn't for us. And then a third group, the real heroes, will struggle through it and figure out how to get it to work, or they'll learn the skills they need to get up and running. But the bottom line is that using a model off the shelf today is like really not easy. And so when I think about like, okay, well, how can we improve now that I feel like I'm part of a community? I feel like I'm helping build these things, make these things better, especially with founding of the company. I think sit back and it's like, there's really two things. The first thing we need to do is like build a culture between models as products. You know, open source has grown, software tooling like NumPy, TensorFlow, PyTorch. These things have taken on a life of their own because both they're the amazing pieces of code, but also someone has spent the time to curate an experience for those users, right? They think of like the API needs to be simple. We think about like what documentation needs to be simple. We think about all those different components. So we need to start thinking about like, what about the users of our models? So what does a developer need to know so they can actually take a model and integrate into an application and use it? What does a data scientist need to know so that they can take this model and actually extend it and use it in some capacity? Simple things like understand like why would I be interested in using this model? So, like I understand that this is based on VGG 16, but like there's no really piece of information that tells me why this is special. Like what is this useful for, and what does it help me do that I couldn't do before? How can I find it? You know, these simple things of just like building a culture and focusing on like discoverability and to focusing on actually being like a product, like a thing you put into the world that you want someone to use. Like how would they get up into running, and how can they extend it, and how can they get the latest version if it's improved upon? But generally, then you sit back and I thought back and in talking with Jason and other people inside our company, other people in the ecosystem, at the end of the day, like the thing we're really missing is we're missing tooling, right? Like these things aren't easy to do. There's a reason this stuff is at the state it is. It's because we're early. It's because it moves really quickly, and we just don't have the tools. We don't have the tools that allows us to package up models, to declare their input and their output format expectations, and to easily move models around. We don't have great tools that just make it simple for us to take a model from this trained in PyTorch and import it to TensorFlow and then top it into like a new serving environment. And we should be able to take any model that's trained on a server and be able to run on a mobile device inside a web page or in a web device. Like, these things shouldn't be hard. Like, it's like once a model's trained, it's a static representation of a graph with some numbers tied to it that you run through. Like, these things, like, it doesn't change. It's not rocket science. It's just we don't have the tools for it. And anyone should be able to take, like, at the bottom of the day, at the end of the day, like, I think the goal we want to aspire to, the place we want to be as an ecosystem, is a library, is that anyone should be able to take an off-the-shelf model and integrate it into their application without having to understand anything about how it works under the hood. I mean, lots of people have no idea how NumPy works under the hood, or lots of people have no idea how like things like React work under the hood, but they can use it to build very incredible applications. So the good news is that there's a beginning here. Like, this isn't like we're not starting from scratch, and there's people out there working on it. And the best representation of that is something called ONNX, which is the Open Neural Network Exchange format, which is an open format for representing deep learning models. It has a tool chain that's super focused on enabling framework interoperability. So that's the ability to take a model that's trained in PyTorch with the TensorFlow or Caffe2 or whichever framework you want to use, like MXNet. Its goal is to allow model training. Its goal is to allow for a workflow where I prototype in PyTorch. I then take the prototype model, move it to TensorFlow, do just training it at a distributed large-scale setting, and then use it, then serve it through TensorFlow serving. It's sponsored by Facebook, Amazon, Microsoft, and I'm super excited that it's out there. This means that we have the very beginnings of our own version of Docker containers to actually enable for models to be moved around, for models to be declarative, and for us to understand and really begin to operate and use them as libraries inside our code, and to give developers the tools they need to build smart applications that we're capable for. So that's what I have. That's my chat. And if there's any questions, I'd be more than happy to answer them.
Well, yeah, we got a couple questions. We'll see if you can hear them, and if not, I'll repeat them to you.
Sure.
For a great presentation, I'm very happy to see that someone is still attempting to sell a model service after AWS and all the rest went into. A lot of developers are going to AWS, Azure, etc. Why do you think you have a chance of beating them?
Yeah, I did hear that. So Dropout Labs is working on private encrypted machine learning. So we're not building a product specifically in this space. This is just like a problem that I think as a team, we actually feel quite strongly about. It's a problem we'd like to solve. We're just not, that's just not in our mandate right now. But I think there's hope, and it's something that I think we want to invest in long term. I think at the end of the day, I don't think developers will stay with AWS. They'll run their compute on AWS. So they'll run their compute on Google Cloud. They'll run their compute on Azure and Microsoft and all these cloud products. And the reason they'll do that is because it's cheap and it's a commodity. But these clouds won't be able to maintain the workflow, won't be able to maintain all the different features that they need to serve all of the different use cases. We're going through, I hate this saying, but I'm going to use it. We're going through the Cambrian explosion in terms of AI research, which is powering us to tackle tons of new use cases. And at the end of the day, the one thing that I learned from watching the boom of the open source community through the Node.js community, or look at the Python package registry, or all of these things that have exploded and enabled all these new different types of technologies and products to be built, is that open things always win because they have way better network effects. And at the end of the day, if someone built a better serving environment than AWS, then we'll just use it and we'll just run it on AWS, right? At the end of the day, all of these tools that everyone needs end up being commodities, and someone will solve the problem. And the important thing is that we talk about it as a community and we start thinking about how to do it. That's sort of my position on it and where my headspace is in terms of I don't think Amazon or Google will own these things. They may own where you run them. So you may pay them to run open source framework, but at the end, I don't think that you will spend a lot of time worrying too much or be locked into an Amazon specific ecosystem for machine learning, or a Google specific ecosystem for machine learning. And if that is true, I think we all lose at the end.
Maybe it'll end up being that we beat them by just being closer to the customer.
Can you repeat that, Jason? I didn't hear that specifically.
Maybe it'll end up that we'll beat them just by being closer to the customer.
Well, exactly. That's exactly it, right? Like, I think that's like the most salient point. And you said it better than I said it in like a minute. Is at the end of the day, the people that are most like that are in the front line that are experiencing the pain or innovating are always the ones that are going to be ahead. Like Google and Amazon and Azure are only going to build products where there's enough people that they can that it's worth it to build the product. They can sell it to enough people and understand that it's going to be a commodity, right? Like that's just the way those platforms work. Is like we understand that AI serving an AI model is a commodity. We're going to build a product there because we can make a cent per hour on serving an AI model. And so their business model is different. So they're always going to be looking at trends. They're always going to be looking to see what startups are doing, what type of models people are doing, and then they'll support features based on like what the most common use cases are. So they'll always be behind.
Yeah, thank you. You know, maybe I'm kind of worrying about the wrong thing, and the real thing to worry about is how do we sell these AI benefits to the customer? How do we sell AI?
Yeah, exactly. And that's the trickiest component, right? Because there's two problems always involved in selling AI to customers, which is one, finding a pain that a customer has that is worth solving, and B, having a model that is like, and training a model that actually solves the problem.
And then 3, convincing them that it does solve the problem.
Yeah, that's actually also like super salient as well. Accuracy is super important, and AI still has a bad rap for being inaccurate. But we're getting there.
Yeah. We have another question.
About the format that you just posted, the paired
Onyx.
So let's say I have a model, and I have this. Somebody gave this model to me, right? And that model was trained. Now I can run it. Okay, they did it in PyTorch. I can run it in TensorFlow, but it like needed very specific data in order to be trained. And don't I need data that is very similar in order to use it? And if I'm able to collect the similar data in the first place, like, I don't know, what can you do with these things if you don't have the data, I guess is my question.
Right. I mean, I think that's fundamentally like the underlying challenge that we have with all of these tools, right? We had that challenge with open source libraries in general. Like you look in the year 2000, no one built open source libraries and no one open sourced them at all because we thought the code was our moat. But it turns out the customers are our moat, and leveraging open source code just made us work faster. So it's really comes down to a question of where do we think data is going? Like, do we actually believe that data is the key to the kingdom, or do you think data will eventually commoditize? Or is there going to be new technologies that allow data holders to sell access to data without revealing the data, so that's easy to generate models, and so that these things become commodities. So these things enable workflows, enable us to solve problems. Today, it's really going to solve problems either internally, where we want to like solve internal workflow problems, where we have a research team that's like playing around with a PyTorch model, and then we want to export it to like into an like full-on data science workflow that goes to TensorFlow serving, like a Fortune 500, or we're going to be used for open models to post them into like a model zoo. That's in my headspace.
So I think also, if you're Google and you have Google scale data, you can train a much better model than any startup could possibly hope to train, right? They just have millions and millions of data points, in a startup, if they're lucky, will get their hands on 10 to 100,000. And they won't be able to train it as effective of a model. But Google trains these models at that scale and then releases them to the public. A lot of the image models that are in production in pretty much any startup that you look at that's doing deep learning for images came from a data set that had millions and millions of data points that they could never collect. So then they generally collect their 10,000 data points and fine tune that model for their use case. And it becomes much more effective than it would have been had they never done that. But right now, you'd have to take a model, train in a specific framework on a particular data type, and reproduce the conditions under which it was trained almost exactly in order to be able to do that.
Yeah.
With Onyx, the hope is that you can take the model and then use whatever tooling makes sense given your tech stack.
That's an awesome point, Jason. I'll just add a little color to that. Like, so the reason that like the Google and the Amazons of the world are building these open models and giving it to people is because at the end of the day, they realize that enabling is that it's better to own the infrastructure that people are using to build apps than to hold on to these models that doesn't allow anyone to build with AI. So Google's play here is like, listen, we're going to build an amazing image net that you can then do transfer learning on top of to solve some use case that wasn't possible before. But you're going to do it all on top of Google infrastructure and pay us to do the training and to do the serving. And so that's their business case. And so their interest really isn't in. So in the case of like ads and search, they may keep those models themselves. But in the case of like, but they still want to release models that enable people to solve problems they couldn't solve before in the hopes that they'll also spend money on Google Cloud.
We have another question.
So you literally read my mind, because that's what I'm talking about. We had a call with Google actually selling the cloud, and that's what the pitch was, that we have all these images. So part of what we do is we're in agriculture, some of the things that we do. So they might want to look at drone footage, right, or things like that. Google has all these images that they can run against. So they've already trained all these models, which is mind-blowing. And then even text or speech to text, things like that they can run. Google Voice, for example, right, that transcodes voicemail. And like they're like, we've already done all of this. And they give the percentages we made. So they are selling these models as, trying, you'll turn them into a product yourself, but yeah, it was kind of interesting actually that they're selling that. You still have to write some layer to it, but it was kind of mind-blowing actually. That's where you can't ramp up. I couldn't get enough people's voices to actually expose.
I think Google's kind of doing both. They're trying to sell machine learning as a service, but they recognize like the long play is getting the infrastructure, like Ian said. So, good point.
Probably just doing both and see what sticks.
Yeah, right. I mean, that does make sense from a business perspective. But I think we all win if the models are free.
Yeah. And I think that's where we'll end up, right? Like eventually these things will commoditize or new technologies will come out that'll enable us to enable for the data to stay safe, for the models to be created. Or we'll just realize that or we'll end up paying people for their data. Like there'll be a way for the data marketplaces are also a thing that exist. They're becoming increasingly popular where so one thing that happens in financials, like big banks are like, well, we have a shit ton of data, right? Like they have an absolute massive ton of data about consumer history. Think about Aeroplans, for instance, not Aeroplans, that's a Canadian thing. I can't think of what an American equivalent would be, but any of these air miles is a great example. They have so much data, but these companies aren't tech companies, right? They don't have the capacity to just turn around and be like, how can we use this data? So what they end up doing is they end up selling the data for someone else, or what they do is they do something called, they basically co-author a model. So they'll create a company with another technology firm, and then they'll say, hey, you can have access to our data, create the model, but we want to own 50% of the result. And so I think what will end up happening is with the rise of these data marketplaces, we'll see that these little spin-off startups that just never really work out will die away. And then big banks and stuff and big companies that have a lot of this data but don't have the expertise and are not the type of company that are not technology companies will just end up selling their data in an encrypted fashion to other companies around. So a small startup, for instance, could buy all of the credit data, behavior data that they would want, but it's encrypted. You don't have access to it. Just the way you train the model is super safe, but you end up with the model in the end. And they get paid to provide you with the data. So I think there's a lot of hope here. I wouldn't prophesize that Google, Microsoft, and Facebook will end up owning the entire world. They do have a lot of data, and that is in Amazon. But I think at the end of the day, what will happen is that new startups will come to solve these gaps, these demand issues, and we'll have new tools that will help us solve a lot of these problems. It's just that we're really early on, which all spells good hopes for open models, hopefully.
We have another one.
Cool.
Ian, a long-standing problem in data science, the most common client is a corporate client, and they have data locked up in different databases, and you end up dealing with that most of the time. Any thoughts on how we get beyond that problem in the upcoming year?
So, Jason, could you repeat the question? It broke up halfway through.
Sure. So the observation is that at a lot of these larger companies, they do have a lot of data, but it's siloed in different departments, different systems, et cetera. In order to do a lot of this stuff, we want it kind of in the same place so we can train these models. What are the prospects on simplifying that process over the next year, say, in the market?
Interesting. Yeah, so that's actually that's actually the reason we started Dropout Labs. Is this specific problem? So I had this. I used to work at Salesforce. Worked at Salesforce for 4 years. We had the same problem. It said like Salesforce is something like 150 terabytes of business data, or not terabytes, like petabytes of business data or something ridiculous. But we couldn't use it to build any AI, despite being like the business data company. That's like effectively what Salesforce does. It sells a giant database in the cloud to other companies to use. And so I think what will end up happening is, I think we'll have encrypted machine learning technologies that'll come out that'll deal with these, that'll tear down these regulatory walls or locking the data up, and companies will feel much more comfortable because there's like a mathematical guarantee behind it that they can leverage these data to produce models. In order to do that, we really need like two things. We need and the name's escaping me, but MPC is one component, which is something called multi-party compute, which is used for doing the encrypted secure computation. And then, Jason, you'll have to help me. It starts with an F, but it's late here in Canada and I've forgotten it.
What's the
privacy tech? The other privacy technology with a budget. I forget the name of it.
Oh, differential privacy.
There you go. So we'll need differential privacy is the other technology we'll need to really enable this to happen.
How would that enable these two things? Things enable the situation that we're talking about.
Yeah, sure. So differential privacy will enable us to anonymize the data set so you can't do statistical inferencing attacks. So right now, if you train a model, right, it's possible to do certain types of statistical or inferencing attacks that basically allow you to say, hey, does this user belong to this data set? Which is one of the components that it reveals. You can use it to reveal the identity of someone inside the data set. So an example is that if you guys remember from 2006, there was the Netflix machine learning challenge where they had like a challenge, like $1 million challenge. Like if you improved it, whoever wins this challenge, like gets $1 million or something. And it turns out that someone figured out how to backwards engineer to get other like personally identifiable information of the data set, despite them actually anonymizing it by cross-referencing with another data set. So that's one thing that differential privacy helps to solve. And then multi-party compute or secure computation helps solve it. Helps solve the other component, which is ensuring that like when you actually are performing a computation, whether it's training or validation or prediction, you're capable of neither party actually is revealed to the data. So what you want differential privacy for is for once the model is generated, if someone gets a hold of the plain text model, they can't do like a statistical inferencing, a membership attack to figure out who is a part of like the training set used to train the model. That's what differential privacy really helps with. And then multi-party compute helps ensure that like when I take a picture of like a mole on my hand, that the person that is actually running the computation doesn't have access to the actual picture. What they get is just an encrypted picture that they can then compute upon. Another example would be in the case of training. If I have a data set that's super sensitive, I can encrypt it, and I can basically give it to someone else so they can train the model. They don't ever have access to the data as long as I've as long as I've leveraged differential privacy to ensure that it's properly anonymized up to a statistically significant level, and that way I never have to reveal the actual plain text data used to train the model, but at the end of the day, they do get the model trained. And so those are like two important privacy preserving technologies, and like that will enable these use cases. That will enable these like silos that exist within these big corporations or between these big companies to come together and actually create models that aren't possible today for regulatory reasons, because like you literally don't want the plain text data revealed to anyone. So that was a long-winded answer. But I feel like we should, Jason, we should come back and maybe just have someone talk about those privacy technologies if more people are interested in them, because that's like its own presentation in itself.
For sure. If there, we have like 2 minutes, so if there's one last question, we can take it. Otherwise, I think we'll. Okay.
I was just gonna say that actually a bigger problem is the whole question, data structure. It's, you see that more than anything. You have all these silos of data. How do you actually bring them together? What are you matching them? It's not even about privacy. It might not even, first, it might be public data, for example. So how do we marry public data and make that valuable to clients? Anyway, you take IBM off the Weather Channel, and then they sell it to farmers. So things like that, that's what we actually see the data problem on our end. How do we just the user, because the users are anonymous a lot of the time for us. How do we marry the data?
Yeah, that's a super important point. I think like I don't think a lot of people, I don't think that problem's being solved is because we stop at like the data regulatory problem of like, it's just a no-go for corporations because they just can't solve those problems for themselves today. And so they don't even want to invest in like, well, in the tooling that requires to like create standardized schemas. I mean, that's my guess. For a long time, we've tried these like public schema things, like even prior to like data science, it's always been like an issue with like the semantic web. Was like, well, we need a standard way to describe like a person. So like Google, when it crawls, can like crawl and understand what this information means about a person that's on a page instead of it just being inside a paragraph tag, right? So I think you're right. That is like a fundamental challenge, and I'm not sure the exact way to get it started. But I do believe the way that we have to start a conversation that like it's worth solving this problem, because once you do, we can bring, like as you said, bring these public data sets together with these private sets, and the private data isn't leaked. So it's a little bit of a chicken and egg problem in my mind.
Cool. All right, I think we're out of time. So thank you, Ian, for tuning in. And
I